All right, so the type of problems I'm going to be talking about are what's called synchronization problems. And we'll see that cryo-EM is one example of this. So as kind of a disclaimer, I'm not the expert on the biology side of this, but let me anyway try to explain roughly what cryo-EM is. So cryo-EM stands for cryo-electron microscopy. So what's the idea? You have some big molecule, maybe a protein, and you want to know what it looks like. You want to come up with a 3D model of it, given a whole bunch of samples containing this molecule. So the kind of classical method to doing this is X-ray crystallography, which means that you have to figure out some physical way to make all these molecules crystallize. So they all line up the same way, and then you can take a picture of them. But this is hard to do for lots of big molecules. And the idea of cryo-EM is instead to just freeze your sample with all the molecules rotated at different random orientations, and then take pictures of them all. And now we have this computational problem of trying to use this data to figure out what the molecules looks like given all these differently rotated samples. So that's kind of the biological motivation for this. So what's the mathematical problem we are interested in? Okay, so there's kind of a schematic picture of this on the left from Amit Singer. So this is like the Mickey Mouse molecule or something. And you can see different 2D images of it from different rotations. So each one is rotated differently in three-dimensional space. So we have an element of SO3 of the rotation group associated to each of these images. And by comparing two images, we can get some idea of what the relative rotation should be. Right, so all these images are very noisy, so we don't have a perfect idea, but we could at least write down some kind of a loss function or get some idea of which rotations are likely and which ones are not. Yep.
So the images that you have here, should I think of them as a shadow or more as like how much mass was in between the image, like the camera and the...
Yeah.
Or as scattered.
Or a scatter, yeah.
That's a good question. I think the answer is that it's more like how much mass. So you do, yeah, it's not just like an outline of the molecule. Like as you can see in these pictures, you do get to see which areas are more dense and which are less dense. Yeah, thanks. And okay, so here's the mathematical question. How would we possibly synthesize all this information to figure out what all the relative rotations should be? Once we have the relative rotations, it's then relatively straightforward to reconstruct the molecule. Because this is now just a matter of sort of averaging the information over all the samples. And we have enough samples that this should denoise everything sufficiently well. So the real hard computational problem here is figuring out what the relative rotations should be. Okay, so what's one very classical method to try to solve this is what's called spectral methods. So let's talk about what that means. So this matrix here on the left is what I mean by a spectral method. So let me just say, so if we're thinking of some group element in SO3, I'm going to imagine this actually as being...
What's SO3?
Okay, good question, thank you.
Not everybody is math grad.
Okay, right, so SO3 is the group of rotations in three-dimensional space. So it's 3x3 rotation matrices. Yeah, so as I'm writing here, each element of G corresponds to some 3x3 matrix that's orthogonal and has determinant 1, which means that it's a rotation in three-dimensional space. Yeah, thanks. Okay, so the matrix that I'm now going to think of as almost my ground truth is this matrix I've written in the left there, which has 3x3 blocks. So this big matrix with 3x3 blocks. So and the blocks represent sort of the relative rotation, right, if I take image I and image J, the ij block is GI, GJ inverse, which is a rotation matrix describing the relative rotation between those two images. So in particular, we just have the identity matrix on all the diagonal blocks. Okay? And so this matrix is 3n by 3n, n being the number of different group elements, number of different images, just because of the 3 by 3 blocks. Okay, and the idea here is that this has some kind of a low rank decomposition, specifically this one, where I just take the blocks G1 through Gn times all their inverses. Right, so this is a rank 3 matrix. And the hope is that given some noisy measurement of what the true matrix looks like, I would then take use PCA, so take top eigenvectors to try to figure out what this low rank decomposition looks like, and then that would tell me about what the group elements are. Okay, does that make sense? Any questions? So this is kind of a basic, yeah?
Sorry, just a clarifying question. So if each of the photos correspond to a group element, so are each photo replaced by a rotation from like a base vector? Like how do you translate from one of those photo slices to a group element?
Right, yeah, so what I would need to do is, so I haven't sort of fully specified how this works, but in order to build this big matrix, I need to go for each ij pair, for each pair of images, I need to somehow construct a guess of what the relative rotation should be by looking at the images, and I put that rotation matrix here. Yeah, thanks. So that the whole matrix is kind of a noisy version of this one that I want to recover.
So it's always ranked. So this matrix, this block thing, is always ranked 3.
Yeah, the true underlying matrix, but not sort of the noisy one that we would observe. Yeah, but we would still hope that kind of maybe the top.
Okay, are you going to get to this, or how do you think of the ijth block, like intuitively? The relative rotation, I see, between the two orientations.
Yeah,
okay.
Makes sense. Okay, so what I want to talk about is, right, so this is kind of a very basic method, and I want to talk about what the limitations are. So why is this not sort of the optimal thing to do? Okay, so the first thing I want to point out is that this ignores the constraint to valid group elements, meaning that I haven't used anything about the fact that each block is supposed to be an orthogonal 3 by 3 matrix, right? So that's some structure that we would hope to be able to exploit. The second one is that we've, in some sense, linearized the observations. And all I mean by that is that we had all these complicated pictures of what things look like we had all this data, and I reduced it down to just a single guess for what the ij relative rotation should be. Right, and somehow that's losing some information, and you would hope to maybe there's more information in the images that I could use than just kind of that one single guess of what the best rotation looks like. Yeah?
The ordering in I, which images fit into which category, those are arbitrary on order, in effect?
Right, so I've arbitrarily decided that this is image 1, this is image 2, all through n. Yeah, and I'm indexing it that way. But yes, it wouldn't make a difference if I used a different ordering. Yeah. Okay, so these two sort of weaknesses lead to some challenges that we'd like to overcome in sort of a better algorithm. So the first one is, how do we use the group structure kind of correctly? And then how do we fully exploit our observations better than just going with kind of a single guess for each entry? Okay, so what I'm going to talk about is I'm going to use a framework called Approximate message passing. So this is a general type of algorithm that's been used in a lot of different settings, and I'm going to apply it to this setting to overcome these type of challenges. So I'm not going to start out by talking about cryo-EM. I'm going to start about talking about very simple toy problems, and then at the very end we'll build up and show how these same ideas really can be used for complicated problems like cryo-EM. Okay? Okay, so here's a very simple problem that is somehow a caricature of what the cryo-EM problem looks like. But instead of thinking about rotations in SO3, I'm just going to think of plus minus 1 values. So I'm going to think of each image just has a plus minus 1 value. Okay, so there's n of these values, and we get some kind of noisy pairwise measurements about the relative sort of same or different values. So here's explicitly what we're going to imagine observing. So this is basically a matrix of noisy pairwise values. To make this clear, let me just write down what is the ij entry of this matrix. Right, this matrix ij so what's going on here? So this is the true, this is like the true relative, not really a rotation anymore, but the relative sign of these two values. And this W is noise. So it's just a normal 0, 1 Gaussian random variable. And by putting this all together in a big matrix, we get a pairwise observation for every entry. Right, and the signal is this rank 1 XX transpose vector. Yep?
Why is the scaling different for the signal and noise? The root or 1 over n?
Yeah, thanks. So the reason this is scaled like this is because as n goes to infinity, I want both the signal and noise component to have spectral norm that's a constant. So spectral norm means just the largest eigenvector or eigenvalue. So the signal term here has maximum eigenvalue lambda, and the noise term has maximum eigenvalue 2. This is just a property of these random Gaussian matrices. So it just means that it makes it so that the noise and signal are comparable in size. So this is kind of a regime where we don't expect to be able to exactly recover the signal, but we expect to be able to get some constant correlation between our estimate and the truth. Yeah, thanks.
So that's an argument that this scaling gives you non-trivial random matrix theory. But why does the scaling reflect the actual problem that you're interested in?
Yeah, so that's something that I can't currently answer with what's on the board, but it is true that, yes, the statistical limits of the problem do obey this same scaling. Yeah.
So like for realistic values of n and realistic amounts of noise that you'd expect. I know this is a cartoon of the actual problem, but you expect these things to interact non-trivially, that the noise is sort of on the same scale, spectrally speaking, as the signal.
Oh, you mean for like an actual cryo-EM problem?
Yeah, it's sort of, I mean, so like, is this scaling relevant to that problem? Because do these scales actually match up in realistic settings?
Okay, that's a very good question. I mean, I think we would roughly expect that to be true because we're not in the regime where we can just perfectly reconstruct. Right, like somehow the other regimes are somewhat trivial. Like either there's just so much noise that you can't do anything, or there's so little noise that the answer is obvious. So at least from a theoretical perspective, this is the interesting regime to study. And yeah, I'm sure that, I mean, in real life, we also expect a comparable amount of the two so that it's not a trivial or impossible problem, at least. And this, so I didn't specify what this lambda is, right? This lambda is just a positive value that indicates how much signal versus noise we have. And that's just a constant that doesn't depend on n. Okay, so is this model clear here? And then finally, just note that we can't hope to learn the actual true vector of x's. We can only hope to learn it up to a global sign flip, because we can only learn the relative plus minuses, right? So if I flipped all of them, it would look the same. Okay, so let's talk about what are some prior methods, kind of building up some intuition towards this AMP algorithm that I'm eventually going to get to. You can take the top eigenvector. So this is the PCA method that I kind of alluded to previously. How would you actually compute the top eigenvector of a matrix? So that's power iteration, which means you just start with some random vector and you repeatedly multiply your matrix by that vector. And then maybe normalize it to have norm 1 or something. And as you keep repeating this, that vector will get closer and closer to the maximum eigenvector.
I'm sorry, I have one more question about the model. Why do you model the entries of the Y matrix, sorry, the noise for the Y matrix as entry-wise independent? Isn't there some correlation, like, so that, what do you actually observe? You're modeling it as observing the entries of Y. Is that reflective of the problem?
Right, so that's a very good question. And that is, yeah, this is a real issue of model mismatch between what I'm talking about here and real cryo-EM. So yeah, this really is a kind of a toy problem. Okay. And I will address this later in the talk about the issues of correlation.
You're kind of more observing X than you're not really observing Y.
Yeah.
Y is a mathematical construction, right? So modeling the noise in Y as IID is kind of, it's not totally obvious that it's the right thing.
Yep, yes, absolutely. You're absolutely right, yep. I will try to touch on this later, yeah. But right, so the power iteration is one method. What's kind of, right, I mentioned one weakness of this approach being that it doesn't exploit the structure, meaning it doesn't exploit the fact that X is supposed to be entry-wise plus minus 1. Okay, so how could we try to exploit that structure? Is that we just round the vector to be plus minus 1 after each iteration. Right, so we multiply by Y, and then we take sign. Right, by sign I just mean positive values go to plus 1, negative values go to minus 1. So we're kind of alternating between trying to align well with the matrix Y and then also snapping back to our constraint. And then I won't say very much about this, but I just want to mention that semi-definite programming is another approach that people use for this, but that's quite a different idea, and I won't talk much about that. Okay, so going back to this projected power iteration. So maybe now, what's the weakness of this? Why is this not the optimal thing to do? The answer to that is basically because snapping to plus minus 1 is too sharp of a transition. Like if the value is very close to 0, depending on exactly where it lies, I might get a huge difference in where I end up. So the hope would maybe to do something that's more of a soft threshold, that more kind of continuously maps values. So instead of applying the sign function after every step, what if I just apply sum function at every step? And it turns out that the best function to apply, so I'll explain sort of why later, but is hyperbolic tangent. It so happens. So hyperbolic tangent looks like some kind of a soft threshold that doesn't snap exactly to plus minus 1, but instead does this type of shape. And we're applying this entry-wise to each coordinate. Make sense? Okay, so what's kind of the idea here? The output of this tanh function, each one is a value between minus 1 and 1, and you can think of it as kind of representing a confidence of like how much do we think this entry is 1 versus how much do we think it's minus 1. So this can be thought of as some kind of Bayesian approach where we're thinking about posterior distributions on each entry, and maybe this reminds people of what's called Bellef propagation. if you've heard of this. So I'm going to switch gears a little bit and now talk about what belief propagation is and why it yields a similar type of algorithm. Okay, so what is belief propagation? Belief propagation comes from the theory of graphical models and is very related to statistical physics. And it's a method for Bayesian inference. I don't want to go into the full details of what the belief propagation algorithm is because it's somewhat complicated and tedious. But to give you a flavor of what's happening, each node is trying to keep track of a distribution on plus minus 1. So it's trying to keep track of like how likely it thinks that it is plus 1 versus minus 1. And these nodes are passing this information to each other and then updating their own beliefs based on what everyone else says about themselves. So more formally, you can see kind of in the picture on the left that this node in the middle receives a message from all these other nodes. And that message is, each node is saying what it thinks itself is as a distribution over plus minus 1. And then this middle node has to consolidate all that information correctly using the matrix Y, using the fact that, like, right, because this node has some idea of like, I think I'm probably different from this node, and probably the same as this node, and probably the same as this node. So using those messages and this information, it can kind of do a Bayesian calculation to figure out a new distribution for what itself should be. There's one caveat in the sort of message passing procedure, which is called no backtracking. So all this means is that if somebody sends me a message at one step, I try not to send back the same information in the very next step. The intuition for this could be thought of as like the way that maybe a rumor would propagate around the room. Like if somebody hears a rumor and they're not so sure about it, but they tell it to me, and then maybe I tell it back to them, and then that makes them even more sure that the rumor is true because they heard it again. Whereas in reality, this obviously is not true, right? So it turns out that the correct way to pass around messages is with this non-backtracking structure, where actually the message that I send to you at this step depends on the incoming messages from all other nodes at the previous step, but not the message that I just got from you. So I'm actually sending out a different message to every node, right? Each node I have to specifically exclude that message when I compute it. Okay, and a lot of these same ideas occur a lot in statistical physics, where they call it the cavity equations. So this belief propagation is expected to be quite a good algorithm, and in many cases the kind of optimal Bayesian algorithm you could possibly have, but it's very hard to prove rigorous mathematical statements about it. So this is kind of notoriously difficult to actually give an analysis of how this works. So here is where the main idea, the approximate message passing framework, comes in. So you can think of this as kind of an improvement or a simplification of belief propagation that works in certain scenarios. So what I need so I need to have a dense graph of interactions here. And all I mean there is just that each node talks to every other node, or at least most of the other nodes, right? So here I have pairwise information about like all or most pairs of nodes, and so they're all talking to each other in this dense way. Something that would not be dense would be if I had a problem on like a sparse graph, where each node only had like 3 neighbors or something like that. But for dense type of problems, it turns out you can typically simplify belief propagation to a much nicer thing called approximate message passing, AMP. And so another step you do in the simplification is sort of by central limit theorem, all these messages you pass around are going to be very nice. Like maybe if you're passing around continuous distributions, they're all going to be Gaussian. And so you can describe these distributions in a few parameters and reduce down to some much simpler algorithm that only involves kind of a finite number of parameters. So this algorithm has been used in a lot of different settings and is known to be the optimal algorithm in many settings. So compressed sensing is really the first time this was introduced by Donahoe, Malecki, and Montanari, and also for various structured PCA problems, so sparse PCA and so on. This is also known to be the optimal algorithm in many cases. And this does allow for a rigorous proof. So this is proof first by Atti and Montanari. So the fact that this is much simpler than BP does allow you to actually prove rigorous results about it, which is good. Yeah?
It's fine if the answer is no. I'm trying to understand how those problems would map onto each other. So is there a simple way to see what the network would look like for compressed sensing or any of those other examples you gave? Or is it's fun, like I said, it's fun.
Sure. In compressed sensing, you actually have kind of a bipartite graph with one side is your nodes, one side is your variables, and the other side is your constraints. So this is a bipartite factor graph. And the nodes are, so the belief propagation is a little bit different, but the nodes pass messages to the constraints, which pass,
So it's an alternating algorithm that kind of goes back.
Right, yeah, the messages kind of propagate through the constraints and back to the nodes. Okay, so now we are at the point where I can tell you what actually is the AMP algorithm, at least for the special case of the Z2 synchronization problem, right, which is this problem with the plus minus 1 values. Okay, so what's going on? This looks kind of complicated. Okay, so this Onsager correction term, let's not look at that for a moment and just look at this first part. So we'll see that this first part is just the same soft thresholding power method that I talked about earlier, right? Here's your observation matrix Y, you multiply it against your vector, and then you apply hyperbolic tangent. You apply tanh entry-wise, and you keep repeating this. Okay, so, and this derivation comes from, right, so lambda, remember, is this signal to noise parameter, which is a measure of, why should it?
The power you would just multiply by the matrix and, right, lambda would be coming out of that.
Yeah, it's true that there's kind of already a lambda here, and this is a second factor of lambda. Yeah, I don't know if I have sort of an intuitive explanation for this other than just you can derive this from belief propagation. So starting from sort of these optimal Bayesian belief propagation update steps, you actually can just derive this in a methodical way, and this is what comes out.
So is this like what you do, or you're saying this is what it is achieving? I mean, you don't know lambda, right, initially, or?
Okay, that's another good point. So for now, I'm assuming we do know lambda, but that's right, that if we didn't know lambda, you would have to estimate lambda. So you could, given just your data, you could actually estimate lambda just based on the variance of the entries of the matrix. Yeah, so this is a totally another issue where, yes, in real life you will not know lambda.
You could look at the spectrum or the norm, and you could get a good estimate if it's big enough.
Mm-hmm.
If it's super critical.
But, right, yes. Yeah, I'm assuming for my purposes that lambda is known, but yes, you're absolutely right that this is another issue. Yeah, so this is the algorithm that you run. You do this soft thresholding power method that I talked about, but it has this weird Onsager correction term named after a physicist, Onsager. And where this comes from is this non-backtracking idea that I talked about. You'll notice that if you think about what the projected power method is doing, that it is kind of like a message passing step, right? Because each node, the new value for each node is like the matrix Y times the old vector. So for each entry, right, you're multiplying a row of the matrix times that vector, which has a bunch of different terms, and each of those terms can be thought of as like a message coming from that other vector.
What are the nodes at the edges?
Okay, yeah, sorry. The nodes are just the 1 through n, like the values you want to recover. So the coordinates, the plus minus 1 values that you want to recover. Okay. So the entries of the vector x, those are the nodes. And I'm thinking of just a complete graph. Like by edges, I mean all the nodes are talking to all the other nodes. Yeah, thanks. But right, if you think about the soft thresholding power method on its own, this actually does have the backtracking behavior, which we don't want. And this Onsager term manages to kind of correct for that. And each entry of this V literally encodes a distribution over plus minus 1. So it encodes it as the expectation. So a value V sort of represents the distribution over plus minus 1 that has that expectation. Right, so that's kind of if thinking about where this is coming from belief propagation. Okay, so now here's just a quick comparison of some different methods. So for different values of lambda, you basically see that the AMP method is optimal over the entire range of lambda parameters, whereas PCA is weak for large lambda, and the projected power method is weak for small lambda. And we also see that this Onsager term actually does help, is actually a real thing we need. And this has also been proven rigorously that AMP gives the optimal mean squared error possible of any algorithm in this setting. So at least for the Z2 synchronization, we provably know that AMP is the best thing you can possibly do. And this is prior work by Deshpande, Abe, and Montanari. Okay, so what most of the rest of what I'm going to talk about is how you can extend these ideas to more complicated problems, right? We don't want to just talk about plus minus ones. We want to really talk about rotations in three-dimensional space and things like that. So let me just quickly give a few examples of other synchronization problems that people care about to get a sense for what types of problems you can solve using this. So this is something called multireference alignment. Basically, there's an unknown signal, which is just a vector, and you get to observe a lot of noisy copies of it, but they're all cyclically shifted in different ways. So here you can see that the signal kind of has this bump here, and then now it's shifted so that the bump's over here, and now it's shifted so the bump's here. Right, so the underlying the group elements that we want to recover are now elements of the cyclic group. So all possible shifts, right? And we want to recover how much has each image been shifted. A similar thing is this angular synchronization, where we now have a bunch of copies of the same picture, but they're all really noisy, and they're all rotated differently to random angles. And we want to figure out what are those relative rotations so that we could align them all and then denoise it to figure out the true picture. So more mathematically, we can think about a synchronization problem over any group. So this is a group in the mathematical sense. So the idea is to learn a vector of group elements. So these are, think of as the rotations. And you get some kind of a noisy observation of the relative group elements. And this is kind of the main contribution of this work. So we give an algorithm based on approximate message passing that can basically solve a very general problem of this flavor. So working over any group with basically any kind of noise model or any type of observations that you want. So I guess basically the next step after just plus minus 1 vectors is this case of angular synchronization of U1. So this is basically just the complex version of the plus minus 1 case, because I'm thinking of U1 as being just all the unit norm complex numbers. Right, so this is just the unit circle, and each point on the unit circle corresponds to some angle. Right, so on the left, remember we're talking about these pictures that are all rotated differently, and those angles correspond to the rotations. So here's a similar noise model to the Z2 case, but now complex. Right, so we have this XX star, which is now the matrix of relative rotations. Right, star is a conjugate transpose. So this simple model behaves similarly to the Z2 case. And for instance, it's been studied already, and semi-definite programming works well here. The real kind of interesting case that is important towards building up to like complicated groups is this case of having two frequencies. So what do I mean by this? Now there's two entirely separate observations. One is just the original thing we thought about, which tells you about the relative rotations between things. And the second one has all these squares here. So by square, I mean entry-wise square. So you have a vector of angles, and you square them, so you double all the angles. So this matrix here is telling you something about the relative squares of angles, which is kind of like the second frequency worth of information. It's additional information rather than kind of on top of this. So the reason we're doing this is because real problems like cryo-EM, you really have information on all sorts of different frequencies in some sense, which I'll get to. And originally, when I said PCA has this problem of linearizing the samples, this is how we're kind of overcoming this, is allowing information to be on all frequencies rather than just the first frequency.
Would you just get entry-wise doubles all around in this case? For the angles? No?
Right, but for an angle, if you know the double of the angle, you don't necessarily know the angle itself. Like there's two possibilities. Yeah, so it's not just redundant information. Yeah, thanks. And in general, you could have any number of frequencies here, where you take entry-wise kth power. Okay, so this corresponds to kind of nonlinear observations. So the type of observations we have in real life will have multiple frequency channels, and it's really not clear what to do with all these channels. Like, it's not clear how you would use something like PCA to try to synthesize the information together from all these different channels. So this is kind of really one of the key challenges that AMP will address. Yep?
Just to make sure I understand, the higher order wise would be totally redundant if you didn't have noise, right? The idea is that it helps you with denoise or something. I mean, you do know the double angle if you know the angle, right? So
yes, that's
like
right.
The other way doesn't work, so it must be that because of the noise, it's helpful to have the higher order information or something?
Right. If there was no noise and you knew the first one, you could then find all of them. But it turns out that the thing we're given in real life for something like cryo-EM really looks more like this, where we have more like this whole spectrum where we have really observations on different frequencies. Yeah. And for this, it's not clear how to really collapse these into just one. Yep.
Is it important that you're writing things with the same lambda for each of the channels?
No, the lambda can be different for each frequency. Yeah, and our method does allow for different lambda on different frequency. Yeah. But yeah, it's important that it's the same x in each example. Obviously, there's one true ground truth, and then the noise is like independent. It's a different noise on each frequency. Yeah. Okay, so what do we want to do? We want to derive the AMP algorithm for this setting. And sort of on a high level, what do we need to do in order to do that? We need to be able to think about distributions over the unit circle, right? Because that's what these nodes need to pass around to each other in order to implement the algorithm. Okay, so how to represent distributions over a unit circle? You could try discretizing things, and this really is not the right thing to do, especially over something like SO3. It gets incredibly awkward. Here's kind of the correct thing you should do is to think about taking kind of a Fourier expansion of the distribution. So if you have a distribution, you have its density function on the circle, and you could expand that in terms of the Fourier basis, in terms of these e to the I k theta. You could also do the same for the log likelihood, for just the log of the density. It's not clear at this point which of these two is kind of the correct one. But let's start by just using the Fourier expansion of the density. And we go through the big derivation. We start with Bellef propagation, and we simplify it to make this approximate message passing algorithm. And I will spare you the details of all of that. But what happens at the end is you get a similar looking algorithm as before. So what happens?
Does the simplifying mean you basically boil it all down to first and second moments in the end or something like that? Is it, you're trying to find like the covariance of a Gaussian using the central limit theorem, or is that roughly what it is? Or?
So it's not true that the higher frequencies disappear. That's what it is just, one of the main simplifications is that Bellef propagation has all this non-backtracking, and it really has like n squared different messages, because each node sends a different message to each of its neighbors, and the AMP boils that down to just n values plus this Onsager correction, which takes care of all the non-backtracking.
Is that still morally equivalent to invoking the CLT and stuff? Like that's what you said at the beginning, but is that
yeah, so the CLT is definitely used in this Onsager term. The reason the Onsager term works is because everything averages nicely, everything concentrates. Yeah, otherwise you really would need to do this complicated non-backtracking stuff, which would make the algorithm more complicated. So roughly what the algorithm looks like is, again, we have some kind of a soft threshold power method. But we do the power method separately on each frequency, right? We have a matrix for each frequency, and what we do here is, we also have a vector v for each frequency, like our vector of observation, our state that the algorithm is keeping, right? And so we do power method on each frequency separately, but then we do a nonlinear function f separately on each vertex, but that combines all the frequencies. So this f here is really where all these frequencies get synthesized together, and that happens separately on each vertex. And what is the f? It turns out, somewhat surprisingly, that the f, that these c's are actually these c's, right? Like these two v's and c's that appear in the algorithm actually are the Fourier coefficients of the density and the Fourier coefficients of the log density. So what is f in general? F is just the transformation from Fourier coefficients of a log density, 2 Fourier coefficients of a density. So that's kind of the general correct soft threshold function that you should apply. Yeah?
So for this, you're assuming that for each of the different frequency channels, the noise is like independent even between them. Is that reasonable if you're looking at a picture of these if you're looking at a cryo-EM?
Right. Yep, that's another good question. Yeah, so definitely there are a lot of various issues here about how much does this model match the true cryo-EM in terms of dependencies among the noise and things like that. I will get to a slide later where I talk a bit about this. But yeah, definitely this issue is probably the biggest weakness of this method here in terms of running it on real data that does not come exactly from these types of models. Yep. Okay, so we have sort of we've sort of derived a general form of what the soft threshold function f should be. And you can go through and see why the hyperbolic tangent function actually comes out of this in the case of Z2. Right, when you just have plus minus 1, the only Fourier coefficient is equal to this difference. So if that value is equal to c, we're talking about a distribution that has like value c on, or we're talking about a log density that has value c on 1 and value minus c on minus 1. And we need to convert from log density to density, so we have to take exp of this thing coordinate-wise, compute the new Fourier coefficient of that, but we also have to normalize it so it's a correct distribution. And this actually is exactly what the formula for hyperbolic tangent is. So here's some kind of empirical results. You can see that this does gain from multiple frequencies. So if I give it 6 frequencies instead of 1, it is able to really make good use of all the different information and synthesize it together and do a lot better than you could do with a single frequency. And it's not so obvious how to do this any other way, really. Okay, so that's concludes the section for the angular synchronization.
Does that plot look really different if you change how much noise there is? Like this is dependent solely on noise, or no? Am I
Right, so I think this plot is made with like the same amount of noise on each frequency. But right, in real life, yeah, there's a question of would the frequency decay somehow and how much and how much signal is on each noise. Yeah, so these are all good questions.
But here you have the same amount of signal on each frequency?
Yes, that's what's being assumed for these plots. Yeah, in real life, maybe that's not a good assumption, but certainly for something like cryo-EM, we expect to not be able to solve it with just the first frequency. Like these higher, like when they run this in practice, they try to use at least like 30 frequencies. So really, they expect to gain from all these frequencies. Yeah.
What's the analog of a power then? Of like taking the integer powers thing, if you're
of the frequencies? Yeah, I will tell you that in about 5 seconds. Yes, so that's the question. How, for a general group like SO3, what are the different frequency channels instead of powers? Okay, so this gets into a bit of more math, but this is called representation theory. So maybe you've heard of this, maybe you haven't, but representation theory basically provides an analog of Fourier theory over any group. So there's something called the Peter-Weil theorem, and it tells you that any function from the group to the two complex numbers, so for instance, a distribution over the group, represented by its density function or log density function, can always be expanded in this sort of Fourier series, where the terms are what's called irreducible representations of the group. So each irreducible representation is like a frequency. And you get terms for each one of these. And you can do the whole same AMP construction as before and get the same type of update step, where again, F is this conversion from the log coefficients to the regular coefficients and so on. Okay, so now I have to justify all the bad claims I've been making about how noise is independent and things like this. So yeah, what I've presented so far is basically that's what we do in this work, and that seems to be very much the optimal thing you can do in the very pure mathematical sense, where you really do have these models with independent noise and things like that. Yeah?
Is that, in the real case, are you actually getting information from different normal modes of SO3 in any sense? In the real problem?
In the real problem?
Is there some sense in which you're getting channels of information that correspond to normal modes of rotation group?
Yeah, I will get to that. And yeah, there is. Yeah, I'll get to how exactly you separate the information into different frequencies. Yeah. So right, that will be coming up right about now. So here's the noise model I have been assuming. So I'm assuming that the measurements are independent on edges. So for each pair of images or each pair of nodes, we have, if we were to write down the log likelihood of a particular vector of group elements, it just has terms that depend on all the pairs, right? And these are independent noise, so they're just a sum like this. So for the real problem of, say, cryo-EM, supposing for a moment I did have independent noise, and that I could write down what these loss functions are, right? This would be based on actually how we compare images and all the physical properties of the system and everything. But we could write down what the actual loss functions are for each pair of images, and then here's what we do: we expand those functions, expand the loss functions using this Fourier basis, and those coefficients are what form the matrices Y. So there's one for each frequency, and these are the matrices we use in the algorithm. So hopefully maybe that answers your question about how you get different modes.
I see. So you take your information and then you project it, or you convert it into the basis of modes, sort of.
Right.
What's the lowercase l again? Sorry.
Oh, the lowercase l is just defined by this. It's just the log likelihood will take this form for some loss function L. And the L depends on what the actual noise model is. Yeah. Yeah, so basically the way the different frequencies come in is by you have some loss function that you're given. It might be complicated, it might be whatever, and you expand that in terms of this nice Fourier basis. And that's kind of what gives you the separation into frequencies. So maybe it's not like there's inherently a separation of frequencies, but it's like this Fourier basis is sort of the right basis to work in.
And then you assume statistical independence in that basis of the noise.
Right, so that's what's required kind of in theory for this algorithm to work. Of course, we can still run this algorithm when it's not true and hope it works. But right, it's definitely true that the noise model we're using here is not quite the same as the real noise model.
So why did you say over any noise model? And like 5-10 slides ago, you were like, we can do this over any noise model. What did you mean by that?
Okay, by any noise model, I mean, yeah. So I'm definitely assuming independence noise, but the actual thing you observe on each edge can be like an arbitrary loss function. So we don't have to just like observe some.
So it doesn't have to be a Wigner matrix. It could be correlated.
Right. It could be. Yeah, you could have, so, okay, for if things are not super independent, then maybe some assumptions of the derivation of the algorithm break down. So it's a bit complicated. But the main point I want to get across is just that, is this idea of having some arbitrary loss function between two group elements. Like you can have any complicated observation model, and you can always still expand that in terms of Fourier coefficients and then run the algorithm.
Does that correspond to some simple generalization of the original model you wrote down?
Yeah, so right, we do define a model like this, where there's like one of these for each frequency, basically. And that's kind of the model that the algorithm theoretically works on. Although you can still, you can still apply it to other things. Okay, so we're basically out of time, so let me quickly finish up. This is another example of just running this on kind of an actual example involving SO3. So the thing we're trying to recover here is now a function on the sphere, which can be represented like this plot with pictures, and what we see is noisy versions of it that are all rotated differently in space. So these are like super noisy versions of this thing that are all rotated differently. Like you probably can't even tell that the signal is here at all. But by taking enough of these and running the algorithm, you can actually like recover what this looked like. Good question. Yeah, Amelia is the one who ran this simulation. I think it was some, 20 to 50 or something. Like it was a bunch. But this is kind of okay. Like in real life, in cryo-EM, we expect to have a ton of pictures. And the problem is really how to synthesize the information. Okay, so here's kind of the ongoing things that we are currently working on or have worked on. And the first one really is this issue of noise independence and things that, the kind of ideal model I've talked about here is really not the correct model for real life. In particular, there's these issues of dependence. There's the issue of there actually being sort of an underlying signal such as the molecule that's not really captured by this type of thing that only looks at pairwise observations. There's the issue that AMP, this issue of needing to know the lambda. So the AMP is quite specific to knowing the noise model. So you would want ideally to have something more robust that doesn't really need to know the noise model exactly.
You have a lambda per mode, right?
Yeah, a different lambda per mode, but we're assuming they're all known. Right. Yeah. And then what's sort of, in theory, the best thing that's information theoretically possible for these types of problems. We expect AMP to match these in some cases, and exploring all of that. Yeah, that's all. Thank you.